Okay, number 12, chapter 7. Suppose a firm has the following production function. Marginal product of this, marginal product of labor, if capital rents for 100, 200. And the firm is minimizing costs. What's the total cost? So what part of 12?
It's like the solution was confusing. It's like 4L squared and then like the square root of Q. Like I don't understand all that.
Okay. Oh, so it was a little, yeah. It was a little,
back, so L ended up being a function of Q, basically, and then something now back into K.
yeah. It was a little more. It was a little more general. All right. So optimal condition, K equals 2L. Hence the production function of the Q units of output is 4L squared, expressed as a function of L. The quantity of labor and capital in terms of production. All right, so let's. So what threw you is just that it was kept in terms since you didn't have a quantity. Yes. Huh? Not now. I mean, it wasn't when Jesse presented, but it is now.
Usually it's a sorry.
That's okay. Don't mind you asking that for sure. Okay, so help me out here. What threw you about? I mean, did you track through the answer key, or do you want me to kind of explain a little bit what was going on there?
You work through the problem.
You just work through it and like be like, this is why.
Okay. You got it. You don't have your. Not everybody. Oh yeah, most of you got your books. And you got the problem there? Okay. Let me go ahead and just put this down. There we go. Not too shabby. Okay, so you get this part, right? The optimal condition, I hope. The one we've been burning through. So slope of the ISO quant equals the slope of the ISO cost line, gives us K in terms of L. So we got 2 times the amount of labor equals the amount of capital. So then the production function.
Hold on, I have a question. Is it because it would be 2?
Yeah, because of the 200. So if you solve that part there, this is 2 over 1, right? The 2's cancel, so the L goes over here. K equals 2L. You see that now? Is that part of what threw you?
So you basically just flip.
Wow, that's pretty good high def camera. Look at you guys can see every.
So you just flip the K and the L.
Yeah. So you got the 2K over 2L. 2K over 2L equals 200 over 100. Well, those, it's 2 can.
So why are you selling for K?
Okay, so then you multiply by L to get it on the other side.
Yeah.
K by, okay.
Yeah. Or L equals 1/2 K if you solve it that way. So it's just one expressed in terms of the other. So then you can go back into the production function. Need it both ways for this? Well, I guess I should go back to what they're. or flip back to what we're being asked for. Oh, because we needed total cost. Yeah, so what is so Q equals 2KL. And then there's the marginal products. And the firm is minimizing costs. What is the total cost of producing Q units of output? So you kind of want to, when you see a problem like that, think about Q units producing 100 units of output, right? But now we're just going to leave it as Q units of output. So Q is actually a number. So that's part of the reason they put a small q here, is just that it's a parameter. So imagine if I would have said 100 units, then it would be the square root of 100 is 10. 10 times 200 is 2,000. See what I mean? So we're just leaving it kind of general for Q units. And then that would allow you to come back to the total cost function of 200 times Q and say, well, what does the isoquant look like for 300 units? Boom, square root of 300 times 200. Right? What is it for 1,000 units? Boom, square root of 1,000 times 200. Is that the logic you're looking for? Okay. And then, you okay with average, marginal? Once we got to that point, it was just kind of getting through that. On marginal. You know, this might be the one.
It's like I was looking up in the book, and it's the average total cost is equal to marginal cost at minimum average total cost. And there was like no work on how that.
There's been a couple problems. I need to think about this for a second. There's been a couple problems where you actually had to use calculus and they screwed up the answer key because they kind of had you do this. So if you've got the average cost, you could use some calculus to find the minimum point of the average cost curve, because they don't give you marginal cost, right? 200Q. This is one of those problems. I don't think you can solve this with algebra to get that answer. So that's happened. There's one other spot where that happened in this book. I'm pretty sure off the top of my head that that's right. Because you've got
Solution online. Like on the ebook, sometimes it asks the site, it says solve this using calculus.
Oh, is that right? I don't know. Yeah, I'm not sure if that one's on here. But you guys won't need to know this for the test, I promise you. But sometimes this happens with the book, that they've kind of put in a problem that you actually would need to do something with calculus to solve it.
So I understand the Q equals 2KL, so it's 2 times 2L, that's 2K times L, 4L squared. And then that next part about quantity of labor and quantity of capital in terms of production.
Here?
Yeah.
Okay?
Can you explain how that was done?
So this is just total cost. So this is total cost equals the rental rate times the amount of capital plus the wage rate times the amount of labor.
Oh, no, I'm sorry, don't worry about it.
Oh, up here?
Yes.
So we had, this is the amount of labor, this is the amount of capital, and this was our production function, 2KL.
Yeah, how did you get L equal to 5 squared?
That was this.
Okay, you just are solving for L now.
Yeah, bring it back the other direction for L.
Okay, how did you, I'm sorry, so for L equals, I see like how you get 0.5K, but where did you get for Q?
So Q equals 4L squared. And then if we, let's see, where does that end up coming down? So you're talking about this step right here. And we had K equals 2L. Q equals 2L squared, right? So then if we go L squared equals 4 over Q, right? How do you get that to L? Oh, yeah, I flipped that around, sorry. Q over 4. I flipped them around. And then how do we solve this? Okay.
That is hard.
As much as you can, I know it's difficult because you guys are just learning this stuff, but as much as you can when you work through a problem like this, think about the basics, the principal basics of what is this Q, what is the L, what is the capital in terms of take it away from being a math problem and put back the economics into it as much as you can. That this is the production function, okay, yeah, I use labor and capital to make stuff, right? And again, I know it takes a little practice to work through. That's why we kind of try to hit a number of different problems different ways. But for what that's worth, as you substitute in, you know, like this step here, you start to say, oh yeah, that's the production function. Now I know that L looks like this, K looks like this, and I can kind of work it through.
I have another question with that. So Q equals 2KL. Up above it says K equals 2L. So how are we getting L equals? I guess I don't.
K equals 2L.
So then you divide by 2 and it's 1 half.
Yeah,
Okay. So then
if you wanted to express it that way. Yeah.
So then half of K times 2K.
Right. So we got Q equals K squared is what we get from substituting this because the half cancels out.
Oh, you plug in the L equation into
Right.
K equals 2L.
Yep.
Oh, wait.
Yeah, they skipped some steps in here, so you guys kind of need to
So you plug in
try to work through it on your
the
own.
function of L into the Q equals 2L. Plug in that 0.5 squared.
As you're solving these, don't go forward until you've kind of figured out the guts in between. So on an answer key, and this answer key is actually pretty good. I mean, it shows you quite a bit of steps. It doesn't show you all the steps, but this is a more detailed answer key than, I mean, they could just say, you know, stuff like this, and then you got to do the rest of it. So, but kind of start from the top and progress your way down, and that's part of the reason I give you guys the answer key so that you can kind of try to fill in those blanks. And if you can't get it, that's what this is all about too, is
Can you
figuring it out.
that Q equals 2KL and how do you get that?
Here,
Yes.
okay, who wants to help with this?
Well, I know that you do like 2K and then you substitute in that 0.5 squared Q for L. That's correct.
Right. So if you take
Wait, no,
if you take this equation, L equals 1/2 K, the 2's cancel out, you get KK.
No, I'm talking about the L that we just solved for that 0.5 squared.
Here?
Yeah.
So you plug that into the L and the production function? To the right of it?
Well, if you did that, you'd end up having a Q,
But that's what
but you can also take, to get this KK, L equals 1/2 K.
Wait, how do we know to do that instead of that?
The quantity of labor and quantity of capital in terms of production.
I mean, I understand like how we get the KK now, but I'm just saying in a test, how do we know to substitute in that 0.5K rather than the 0.5 squared Q?
Oh, well, think about where you're trying to get down to.
I'm trying to get them to the K
So-
without any
Go back to what the question was asking was, what is the total cost function? So you kind of have to know that at the end of the day, I'm trying to get here. And what do I need to get rid of? I need to get rid of the K, and I need to get rid of the L. And so you had to do these manipulations to get that just in terms of the Q. So you had the L here, so there's L equals this. And now you've got Q equals K squared. Take the square root of that, and you get K equals the square root of Q. Now you plug both of those in to get this answer. Let me show you the steps. All right, so this is where we're going. So you kind of had to think about, well, what do I need to get there? Here's my L part, which I hope we're all right with, right? So we get 200 times 0.5 square root of Q. Everybody with me there? And then we've got K that I need to get rid of. We determined, hopefully you're okay here, that Q equals K squared. So K equals what? The square root of Q. So K is the square root of Q. 100 square root of Q, 1/2 of 200 is 100. 100 plus 100 equals 200 Q. It all collapses down to that. So that's why we wanted to, I think it sounds like the thing that was throwing you here was we solved for Q, but you needed to solve for K to plug it in here.
I see understanding how Q entered the equation and now it makes sense.
Okay. And again, it kind of comes down to knowing where you're going with it.
Okay.
So on a test, if I said solve for the total cost, I think before you even really get into the guts of the problem, you might have wanted to do, you know, this. And then you kind of go, okay, what do I need? Oh yeah, they gave me this was 200 and this was 100. So now I need to get this. And all I got is a production function to work with and the marginal products. What should I do? You know, kind of try to reason it out that way as best you can. This is a tough question.
So now you're thinking for B, you're thinking
The average, so just divide it by Q.
what's that 200 square root of Q
Yep.
over Q? I mean, why does that 0.5 Q to the 0.5 go in the bar?
Yeah. So 1/2 minus 1 equals a -1/2. 1/2 minus 1.
Oh, so you're just
And then you're bringing, you could bring them up. So the exponents you subtract in a division problem. So 1/2 minus 1 equals a -1/2, which is Q to the half in the bottom. Those are the little exponent tricks that,
So you have to subtract the division. And are you subtracting the top from the bottom or the bottom?
it's always the top minus the bottom.
And it's negative to the one. Drops to the one.
Yeah, if you have a, so that's one of our cheat sheets. Maybe we should, I don't know if we should attempt to do this right now or not. Why don't you guys pull out a piece of paper? This won't take that long, and then I will have it in my permanent notes forever, in theory.
And then you said it just hit C.
I think that's the correct.
You did?
Yeah.
What'd you get?
Okay, well, do you know how the marginal product and derivative, marginal product and production are the first derivative of the, well, partial
Yeah.
derivative? Okay. The marginal cost is a partial derivative of the total cost. That's it. It's just.
No, I know that.
That's it. You just take the total cost function on this one.
And take a derivative.
Take
of
the
it.
derivative.
That's what marginal cost is, but
Yeah.
that's not for this class.
No.
We're not doing
It's
derivatives.
so much easier to do the derivative.
That's my point, is that you can't, I don't think you can solve for this without doing
No.
the derivative.
Okay.
That's
So-
so easy.
But yeah, that calculus, believe it or not, I know it does make some of this easier. But if you really understand the fundamentals of what we're doing through this class with an algebra-based approach, you actually understand the economics maybe even better, possibly, than, oh yeah, I've just memorized that I have to take the first derivative of the cost function. Well, what does that mean? I just memorized that I have to take the derivative of the cost function. When do I do that in business? Never. Sorry, you don't. You don't do first derivatives to maximize profits in the real world. Now, that doesn't take away one iota, to me, the importance of kind of knowing that thought process. So I'm not trying to downplay it, but I think you get a little more econ out of the algebra-based approach as opposed, because I remember I wasn't a huge math guy, and I remember being kind of lost in the math. I know you guys are sometimes struggling with being lost in the math, but that's okay, but you know, we need to work through it. I think it'll help your understanding of this stuff more as we work through problems.
So the total, yeah.
Okay, what was the other? Oh, we were doing the cheat sheet. So, let's just do it. It won't take too long. I don't know if this is the best place for me to write this or not, but. So, math, basics for intermediate econ. Let's see, what's some of our basics here? So the one we just did is, oh gosh, I'm not very good at doing math. So let's go k to the negative 2 equals, and I could use x's and y's, but I think it'll be easier maybe to do this. K to the negative 2 equals 1 over k to the what? Squared.
So then, if it was k to the negative 0.5, it would be 1 over square root of k?
Yes. So k to the negative 0.5 equals, I'm going to do one even better. Let's put in the one that you just did. K to the 1/2 over k to the, maybe we should just put k without putting the 1 there. And then we'll have another reminder that says k equals k to the 1. There's always a secret 1 there that we never put. K to the 0 equals 1. Anything to the 0 power always equals 1. Which kind of means almost like this is, and by the way, this might not be too bad to, on this one, add k to the 0 power over k squared. Check it out. 0 minus 2 equals negative 2. Okay?
For that k to the negative 0.5, so you said that would lower down to 1 over k.
On k to the what?
K to the negative 0.5. You have it as k to the negative 0.5 over k. That
Yeah.
would also equal 1 over.
This is a true statement right here.
Yeah, I know. I'm just saying, would that also equal 1 over the square root of k?
1 over the square root of k, yes. So if we want to put 1 over k to the 0.5, all those expressions are equal to each other. Okay, what other ones have we missed? Adding, we haven't done adding. So k to the 0.5 times k to the 0.25 equals k to the 0.75. You add them. And k to the 1.5 plus k squared, or times k squared equals, oops, k to the 3.5. All you're doing is adding the exponents.
You can do the one with parentheses, you multiply the exponent.
Say that again?
The one with parentheses, where you have like a
K to
variable
the 1/2
base,
to the second power.
and then outside parentheses, raised to the power.
Oh, So, help me out, k to the, what do you want? K,
One
K to the
half.
second.
k to the 1/2, and then all this raised
Raised to 2 or
to
something.
2.
And then it's 0.5 times 2.
Okay? What does that equal? I'm glad you brought that one up. K to the 1, right? So you're multiplying those equals k to the 1. Might have been better to almost take a different one than that one, but
If that's negative, it's not.
and if it's negative, it'll drop down.
What was it we talked about Monday where it was just the basic rule when you have your marginal products and they equal 1 or if they're less than 1 or if they're greater than 1. If they're greater than 1 then you have diseconomies of scale. Is that what it was?
Oh, that was with the returns to scale thing
Yeah.
on the production function. Yeah, I don't think I want to put that here, but yes, if this, like this example here, and this would be with L and K, not,
Yeah, yeah.
so if the exponents added to 1, it was constant returns to scale, less than 1, yes.
There's also one where you add another set, so k to the 0.5 squared plus, and then do another expression like k to the 0.2 raised to the second, and you add 2 together, so you have 2k. You get what I'm saying?
No, but I'll just work it out. Go ahead,
So
K,
to the 0.5,
okay,
and raised to the second power.
squared, so
Yeah,
parentheses,
and then plus
squared plus,
k to the first power, and you raise that to the third. So you're adding 2 expressions together.
and you think that equals what?
So then it simplifies k to the 1, k to the first power plus k to the third equals. See what I'm saying?
You can't add those though, that's what
So
I'm
this would
afraid
be
you were doing. So this would be k to the 3rd power.
You can't add those together.
No. But you can do this possibly, equals, since we're doing something, k times 1 plus k squared would work, just to show one more manipulation.
Sorry.
That's okay. That's why maybe it's good. In future classes, I'll just give this cheat sheet out, maybe. Well, not maybe, I will, maybe even more though.
I think it's helpful if you walk through it with them.
Like what we're doing now?
Mhm.
Okay.
What if it was like k to the 0.25? Is that like simplify down to anything, or how
Nope.
would it just stays at k to
Raised to the 0.25 power.
Okay, there's no, you can't like that.
You could manipulate it backwards and make it more confusing, but yeah, it's to the 1/4. Yeah, maybe that would be worth
You know what I
putting one
mean?
down.
It's just like
K to the 0.25 power equals k to the 1/4 power.
Well, yeah, but I mean, like, you can't simplify down to like square root of k. It's like and nothing like that. It's just
It's
that
the
is
fourth
far
root
as
of k.
Yeah, 4th root of k.
So the rule is that the 4 comes out, becomes this one.
All right, that's a good review. Let's just stop there. I think that we've hit enough of them anyway. Any other problems from
You know
this
that one that,
homework?
we were talking about with the 17 with the k, it keeps closer than 44, and then it's k is greater than 4.
Which one?
17.
17. The builder. So a builder, custom motorcycle, has a choice of operating out of 1 garage or 2, and it operates out of 1 garage. Average total cost is this. If it operates out of 2, its average total cost is given by this. What does this firm's long run average total cost curve look like? Okay, and what's your question?
Like once you figure out that q equals 4, then it says like, the first average total cost curve if q is less than or equal to 4, and then the second average total cost curve q is greater than 4, like how do you figure
Yeah.
out which one goes with which?
Yeah. So this is what we did last class, was it, with the medium large firm, which I don't think Katie was there, but let me just give you the snapshot, because that's what this problem's like. Well, here's the picture of it. There's actually an infinite number of these short-run average cost curves, depending on where you'd optimize. They gave you a discrete problem with this size garage or this size garage. And so where would you want to be? Well, if you're producing a quantity of 5, you'd want to be in this size garage. It's possible that you could do that much work out of the smaller garage, but it'd be more expensive. So, however, if your business drops down to 3, you're better off in the smaller garage. It's possible, of course, to do less business in the bigger garage, but it's going to be more costly.
Oh, I get it now. It's saying that if it's like 4 or less, you're going to go with this.
You're going to go with this
If
one,
it's
yeah.
4 or more, you're going with, okay.
So the long run average cost curve is the outer envelope of the short run curves.
Okay.
And so the picture, kind of the textbook picture, is that there's an infinite number of short run curves that look like this. And so if we take the outer envelope of that, that ends up being the long run average cost curve. Okay, other questions?
Yeah, can you go over the last one?
Last one. 19. Suppose that a firm has the following Cobb-Douglas production function. So what do you notice about those exponents? They add to 1, okay. What must its long-run total cost curve look like? Its long-run average total cost curve. How does your answer change to part A if the firm's production function is Q equals KL? All right. So, Cobb-Douglas production function exhibits constant returns to scale. Hence, the long-run average cost curve is horizontal, whereas the long-run average total cost curve is a straight. Whereas the long-run total cost curve is a straight upward sloping line. So, because what's returns to scale? Constant returns to scale. This is what Blake was bringing up a little bit. What did it mean to have constant returns to scale? Katie?
As output increases, long run average total cost decreases.
No, that's economies of scale, which is a kind of a kissing cousin to this, but not the same thing. So that's economies of scale. What Taylor said was when you increase the scale of production, the average cost falls. That's economies of scale when you bring the dollars into it. Returns to scale was an engineering concept. It was a physical relationship. I think I gave it to you guys. It should be in your notes. If it's not, then we need to make sure it gets in there. You're close. So Blake says increase capital, output stays the same. It's more than that. It's a long-run concept. True. In the long run, all inputs are variable, and so returns to scale is tied to that. There you go. What is it, Adam? Double all my inputs, I get double output. So if I'm a McDonald's chain, and I open up a McDonald's right next door, same building, same fryers, same freezers, same amount of people, same soda machines, same everything. If I plunk and double everything, what happens to my productive output capacity? Double my inputs, double output. Constant returns to scale. Now, that's not the only possible outcome, though. And then here's where maybe this is a good part to talk about how it's a kissing cousin to economies of scale. If I double all my inputs and I get double output, what's likely to have happened to my cost? If I double all my inputs, what happened to my cost? They doubled, right? So that's where you get that constant cost. So I double everything, I get double cost. Double inputs, double cost. Now, the thing that's missing out on is the two theoretical possibilities of even if your price of the resources stay the same, what might happen to the output? And so there's two other cases. Double my input and I get more than double output. Increasing returns to scale. So you're getting more, so the scale of production went up and people are more productive, there's more specialization. I mean, we could tell a number of different stories, but it's a possibility that you're able to get more than double output. And because you're getting more double output, you're doubling your cost, but you're getting more than double output, your average cost is going down, right? So if you double your resources and it doubles your cost, but you get more than double output, if I now take that bigger amount of output and divide it by all those costs that went up by 2, my average cost goes down. And that's the linkage, that's the kissing cousin part to economies of scale. If I double my input and I get less than double output, I have decreasing returns to scale. So now I've gotten a little bit too big. Maybe I'm facing a management constraint. Maybe I'm doing something else. And so that's causing my average cost to go up potentially. Now, what could be happening, the reason why we separate out those two concepts is because as part of doubling your inputs, maybe you can get a better pricing from your resource suppliers. So you were paying $100 per ton of steel, and now the steel manufacturer that you're a big player for them is willing to give you a 10% discount. And so now you're buying steel at $90 a ton rather than $100 a ton because you're a bigger player in it. That possibility leads to, even if there was a little bit of increasing or decreasing returns to scale, the dollar savings in cost might offset that. And so just because you have increasing or decreasing returns to scale, the result could be different depending on the circumstances on the cost side, which we don't know. We can only assume as we build an economic model that maybe that stays fixed. But in reality, it might not. So when we think of economies of scale, think cost. When you think returns to scale, think engineering, the physical relationship. Double my inputs, double my output. If it's economies of scale, what's happening to cost as I increase scale of production? Two separate concepts. All right, folks, we are out of time. I am going to give you the